Hi, this is Barrett Givens, and in this video for topology, I want to talk about a slight modification to the definition of continuity that is convenient for us to use, and then do another example of how we can check if a function is continuous. Okay, so here's a theorem. Let's let f from x to y be a function, and I'm going to say then f is continuous if and only if whenever u is a basic open subset of y, then f inverse of u is open in x. So how is this different than the standard definition of continuity is that I've added the word basic right there. I've added the word basic right there. So I'm not going to prove this theorem in this video. We're just going to use it. But the important thing is that by limiting ourselves to just basic open sets, it makes it easier for us to prove that a function is continuous. So this is a very helpful theorem. We have our definition of continuity. This theorem gives us an alternative characterization of continuity that is easier to work with in proofs. Okay, so let's see what that looks like. So here's an example. Let's show that the function f of x equals 3x minus 2 is a continuous function from the reals to the reals with the standard topology. So the reason this theorem is useful, well, first of all, do we believe that that function is continuous? Like, does this match our idea of continuity from calculus or real analysis or algebra? What kind of a shape is y equals 3x minus 2? If I were to graph it, it's a straight line. And certainly I think of straight lines as being continuous. I can draw them without lifting my pencil off the paper, right? That's our very intuitive sort of high school definition of continuity. And in real analysis, we would have showed that this was continuous using an epsilon delta proof. So we would have looked at something like x minus y less than delta, f of x minus f of y less than epsilon, something along those lines. Um, but now we're going to do it using the topology definition of continuity. And because we have this theorem, here's what I can do. All right, so let's first suppose f of x equals 3x minus 2, and f is a function from the reals to the reals with the standard topology. So if I don't write down what the topology is, we should assume it's the standard topology. Now, the definition of continuity says whenever u is an open subset of y, but then this theorem lets us modify that to a basic open subset. So whenever, that's like if, right? That's our hypothesis. So we're going to let u be a basic open subset of the reals. So what's nice is that since we assume it's a basic open subset, then that means that it is an open interval. If I couldn't use the word basic there, I would just have to assume that U was a union of open intervals. And I could still do the proof, but it would just be like slightly more annoying, okay? Just a little bit more complicated. So I'm going to assume U is just a basic open subset of the reals, so it looks like an open interval A comma B. Now I want to know what is F inverse of A comma B? What is the pre-image of A comma B under F? Using the definition, this is the set of all x in the reals such that f of x is in A comma B. That is the set of all x in the reals such that A is less than 3x minus 2, which is less than B. So that's using what f is by definition. It's 3x minus 2. And the definition of the open interval A to B saying that something's an element of A comma B means it's between A and B. And now I can just kind of keep rewriting this set using basic algebra. It's the set of all x such that A plus 2 is less than 3x, which is less than B plus 2. And that is the same as the set of all x such that A plus 2 divided by 3 is less than x, which is less than B plus 2 divided by 3. So that's the set of all x between those two values. Well, that's the same thing as the open interval A plus 2 over 3, comma, B plus 2 over 3. And that's an open set. So what have I done? What have I done is I have started with a basic open set. I found its pre-image, and I showed that its pre-image is also open. And since the open set I started with was arbitrary, that means the pre-image of every basic open set is open, and hence F is continuous using this theorem. Okay. And I think you could probably convince yourself fairly easily that any function of the form f of x equals mx plus b is continuous. It would be just like this. I guess if I were using mx plus b, I couldn't use the letter b in my interval also, but I could switch some variables around and make that work. Um, and so this is a really nice definition of continuity to work with. In a lot of ways, this is much easier than the epsilon delta definition of continuity. Um, and, students really struggle in real analysis to use that epsilon delta definition of continuity. And so this one, I think, is in some ways a lot easier to work with. Okay, thank you for listening.